All right, welcome to video number 5. And in this video, we'll be covering box plots and histograms. And this video is a little bit different from the previous 4 videos that we looked at because in this video, we'll just be looking at the distribution of a singular variable across our entire data as opposed to finding relationships or correlations between two types of variables, which you guys saw with line plots, box plots, etc. So essentially, box plots and histograms are useful to help describe the distribution of a continuous numerical variable. And essentially, they both represent how the distribution of our data looks across all 3,000 rows of our data frame. So if we choose our variable in question to be, for example, take the runtime of our movies, through using a box plot and a histogram, we're able to see how our movie runtimes are distributed, where the average, like what the average runtime of a movie is, where the outliers are, all that kind of stuff that corresponds to a distribution. And because they describe the numerical distribution of some variable, it won't be extremely useful in understanding the relationship between any of these variables and take, for example, movie revenue. So this is just a little bit of a add-on section that I wanted to talk about just because of its its usefulness in statistics. So the first thing I want to talk about is a box plot, and essentially I drew a sample box plot right here, and the code for a box plot is mentioned right here, and essentially what I'm outputted is this little distribution right here. And this might seem like common knowledge, but for those of you who don't know, I just wanted to go over this really quickly because this is really important in figuring out the distribution of our data along with the histogram. So if you see this orange line right here, all the data in our histograms are represented by percentiles. And essentially, the 50th percentile is the median of our data, which is represented by this orange line right here. And what I mean by the 50th percentile is that 50% of data lies above this point and 50% of our data lies below this point. So take, for example, our case in runtime. So I would estimate the median to be about 105, say, for example. And essentially, because 105 minutes is the 50th percentile for runtime, we're basically saying that half the movies have a runtime over 105 minutes and the other half have a runtime of below 105 minutes. And that's what's basically the orange line is represented. And the orange line is contained within this little bit larger triangle. And this triangle describes the interquartile range of our data, which is basically the middle 50% of our data. So for this to be the middle 50% of our data, the two ends of this little rectangle have to be the 25th percentile and the 50th percentile respectively, because 75 minus 25 is 50. So the 75th percentile, we use the same exact logic as the 50th, in that the 25% of the data lies above it and 75% of the data lies below it. So our 75th percentile for the runtime in movies, I would say, is about 120, 125 minutes, versus the 25th percentile is just under 100 minutes. So that's going to be really important in describing the statistical significance of our distribution. That's what this interquartile range is describing. And then this upper bound right here that you can see that's distinguishes by this line is basically the upper bounds to our normal data. And that might sound a little confusing, but what I mean by that is that all of the outliers we have, which is calculated through its own independent statistical calculation, all the outliers we have lies above this little bar, and all the outliers we have also lie below this bar below this rectangle. So essentially, all the outliers are represented by these little circles here that are shaded in over here and just not shaded in there. So essentially what this graph is telling us is that we have more outliers with a higher runtime than outliers with a lower runtime. So basically, this is saying that movies tended to be longer on average than they did tend to be shorter. So that's the statistical significance of a box plot. And a box plot is really important, again, because it describes distribution, and we can get a lot of different things from this, like the interquartile range, or the 50th percentile, or the 75th percentile, and there's a lot of cool things that we can draw from this box plot. And essentially, a box plot is, like I said, it's really useful for determining percentiles. And there's a really basic function that I just wanted to introduce to you guys in um, Python that we can run is np.percentile, and our first argument would be the column in our table, so revise movies of runtime, and our 50th percentile would we just represent it as 50. And this would output 104. And as you guys can see, this orange line right here, which I said was the 50th percentile, it looks awfully close to 104. Say we wanted to find the 75th percentile. That would be 118, which is represented by this little upper rectangle right here, the upper length of the rectangle. And the 20th percentile, 25th percentile, I would estimate is about 95 or so. But let's just check that out. 94, perfect. So that's just a little bit of how you would find the percentile. And if anyone's curious in how to find which points are considered outliers in our data set, you guys can always take a look at that on Google or whatever. But just for time purposes, I won't be explaining that just now. But that's essentially how a box plot works. And if you guys can revisit the code to write a box plot in matplotlib is plt.boxplot, and because we're just describing the distribution of a single numerical value, we just pass in our indexed column, which is runtime. So that's how a box plot essentially works, and how you would write the code in matplotlib. And a histogram, let me just write the code for that real quick, and I can explain what that is right after. So the code is plt.hist, and then we'd index into our column of runtime. And then our second argument would be the bins, which I'll explain in just a moment. And we can take a look at that graph. Okay, so essentially what our histogram is that a histogram is a visualization that also describes the distribution of some data, of some numerical value, but it's a little bit more flexible than a box plot. And what I mean by that is that the y-axis of a box plot typically represents, some sort of a count. While the variable on the x-axis is our numerical variable, which is being measured. So, for example, this box plot I drew, which is based off of the movie runtime. So basically, what I do is I divide up a movie's runtime into different bins, and the bins go on the x-axis. So the bins are basically how many movies had a runtime between 0 and 50, how many movies had a runtime between 50 and 100, 100 and 150, 150, 200, etc. And the count of those movies are displayed on the y-axis, as you can see over here. So between 100 and 150, there are about, I'd say, 1,700 movies that we can see in that range. So that's the really cool thing about a box plot. It can tell you how many specific movies are in a desired range of some variable in question. We're able to construct bins of varying length through this function called np.arange, which basically is a function that takes in 3 arguments. The first argument is our start, the last argument is our last, or our end, and the third argument is our step size. So in this case, because we drew the box plot of runtime, we can see that the movie with the shortest runtime has the minimum of 0 minutes. The movie with the largest runtime has a runtime of almost 350 minutes. So to construct my bins, I drew, I had it start at 0 and end at 350, so it would capture all of our data. And then a good step size is usually something that divides our interval into 8 to 10, 7 to 10 in that range. So 50 in particular, if we multiply 50 by 7, we get 350, which is the range of our data. So this would be considered a good bin length for runtime. So That's essentially what a histogram is. So again, if we wanted to find the percentile of anything in our histogram, we could use the same exact function that we observed uh, just now, which is np.percentile. But a histogram is a little bit more better in that it shows you that it's a little bit more flexible than a box plot in that it shows you uh, how, how many of our data points or data um, values lie between a given range of some variable, which in this case is the runtime. But before we move on, I just want to talk a little bit about this box plot right here. So the way we're able to determine um, how a distribution looks is its skewness. And I'm not sure what your experience is with this. If you've taken data 8, you should know this perfectly fine. But if you have not, skewness is basically how variable our data is. So if our data falls within a normal distribution, which is a bell curve, and I'm sure you guys have seen what a bell curve is. It's basically a curve that is really high in the center and really low on the edges. If our histogram falls within the normal ranges of a bell curve, it's considered to be a normal distribution. If one side is really tall and the other side is really short, then that's considered to be skewed. And it can either be skewed on the right or skewed on the left. So with this histogram, and usually with a histogram, you want to be able to tell if our data is skewed or not. And in this case, with our histogram, it's really hard to tell whether our distribution is skewed or not because, I mean, because we tried graphing our values to capture the entire interval from 0 to 350, it was really hard to get some sort of a distribution category for this. Like we aren't able to tell if this is normal or if it's skewed just because there's not enough data on the edges or on the sides to be able to tell anything about this data. So in cases like these, if you're trying to use a histogram to find how variable a data is by trying to find its skewness, you usually wouldn't need to have to include all of your outliers, if that makes sense. Usually a good histogram is descriptive of all your data, but in cases like these, when you have like a singular movie that's like almost 100 minutes more than the second longest movie, you really don't need to include this variable in your histogram because it only limits because it only increases the how big your graph is, like the ranges of your graph. Like this graph is from 0 to 350 or 300. Like we could have easily just limited this a lot more, so we can get a lot more of a concentrated view of the data points that really matter. So in this case, we're really not going to need anything above, I would say, like this endpoint right here, which is about 220. Like these two are really high off outliers that I say don't really contribute to our data set as much as we would want them to. But you have to be really careful in excluding outliers when graphing a histogram because it can have some statistical consequences sometimes. But in this case, because we have a data set of about 3,000 rows and we only have two values that are really, really weirdly distributed, I would say we don't need them and we can make our graph look a lot more cooler. So we can just have our bins start from 0 and go to 220. And because our range is a lot smaller, our bin size should also be a lot smaller. And in this case, a small bin size would be really good because there's a lot of data that's stuck. Like 50% of the data is between these two values right here, and these two values are so close to each other that we would want small bins so that we can tell how distributed is this data exactly. So in this case, I would suggest we use a bin size of like 10, 15, 20. But for time's sake, we can just use it as 20. And then we would just use the same exact code as we did before. And then we would clarify our bins to equal the bins that we defined here. Same with this. This bins is referring to this right here. And then once we show this plot, we can see that now we get a much better distribution of our data in the sense that we're able to tell that this data is distributed very, there's a pretty big skew in our data. And this actually confirms my original hypothesis because if you remember, I was saying over here that movies tended to have a lot longer of a runtime than they did shorter of a runtime, because if you can see that there's a lot more outliers above this final bound right here, whereas there's only a few down here. So I think this histogram makes perfect sense because it accurately reflects our data points, and the bins are small enough so that we can see how our distribution actually looks. Um, so here we can definitely tell that our distribution of runtime is pretty skewed. So yeah, that's how we would draw a histogram in Matplotlib. Okay, so let's now reproduce the same exact thing in Seaborn, except this time I want to take the distribution of a different continuous numerical variable. And let's take the distribution of popularity in this case, just so we can see how, because remember how we mentioned popularity is, we didn't think that there was a standard metric for popularity across these 30, 40, 50 years. So I'm just curious to see how the distribution of popularity really looks, and let's try to do that in C1. So I'll draw that right now. So essentially our code in Seaborn for a box plot is going to be sns.boxplot. We're going to put the table name, so revised movies, and then we're going to index in to our columns, which is very similar to what we just saw in Matplotlib. So if we wanted to plot the box plot for popularity, we end up getting a graph looking like this. And to be honest, this graph is all not too great. It's not a really good estimator of how our distribution really is, just because everything is so like cluttered. But we can definitely see that this looks a lot like our first graph, in that there tends to be movies with a lot higher popularity than lower. So I would also guess this graph to be skewed as well. But we can actually check that more specifically through using a histogram, just like we did in our previous example. So if we want to look at a histogram, the code is sns.distplot instead of bar plot. Sorry, instead of hist for a histogram. So the same exact arguments, you would index into popularity, and we would set our bins as equal to something we defined before this. So say we define our bins, because we have very few data points above, I would say like 60. I say we can safely define our bins to be to start at 0, end at 60, and have a interquartile range, or to have a bin length of 6. That would probably be a good estimator. So we would set that equal to bins, and we would plot our graph. Sorry. What's wrong here? Oh. Okay, and when we do that, we end up getting a histogram that looks like this. So it's really Seaborn is not as strong as Matplotlib when it comes to displaying histograms, for example, just because in Matplotlib, when we specified our bin length, our graph was only captured that range of bins. So for example, when we described our bin length to be 0 to 220 with a bin length of 20, our graph only had a range from 0 to 220. But the default in Seaborn is that we're going to look at all the way from 0 to the end of our data, which if we take a look at our box plot ends all the way at 300 almost. So even if we choose the bin length to be about 6 in a range from 0 to 60, it will in fact draw our bins, but it won't include, like, our range will be set to the range of our data by default, which isn't a really good measure. So essentially with this graph, we can definitely tell that our data is very skewed to the left just because of our outliers, because we have some data points that exist, as you can see, like right here, right there, very subtle lines that are like all throughout here. But if we ignore say are outliers, which I say would be totally fine in this case, just because there's so few of them. If we ignored our outliers, our graph looks like a great normal curve. If you guys can see it, it's like normally distributed, goes all the way up, comes back all the way down, and it's a pretty good normal distribution in terms of the popularity, which makes sense that movies on average tend to have an average popularity, um, and like that makes total intuitive sense. So um, yeah, so great job. You guys have learned up to now. You guys have learned how to uh, graph the distribution of variables and understand how to interpret box plots and histograms. And you've also learned in the previous 4 videos how we can find the correlation between 2 different variables or more. So thanks for tuning into this video, and I'll see you in the final video coming up next.